Hey everyone, this is for stats243B, and this is on confidence intervals. This is just kind of a big idea for week number 2. So just big ideas. Not a lot of calculations. We will do calculations more Wednesday night if you have questions. All right, so what's going on here? Well, let's say you have this whole population of people, measurements for people or something, all these different people. Well, you really want to know each one of these people has a measurement. Maybe we're looking at some sort of IQ today, and each person has an IQ. We want to know, hey, what's the true average IQ? The population, this is what we're looking for, IQ. Well, we know from other studies, from our studies elsewhere, that that if we want the best point estimate, then we just take the mean, right? So if we say, hey, the mean is our best guess, the sample mean. We take a sample, we calculate the sample mean, and we say this is our best guess for the population mean. But that's super specific, and therefore being super specific is not terribly likely to be accurate, right? Because it's just one number. When you take one number out of all the different possible numbers it could be, it's a pretty small chance you're actually going to hit the right number. It is our best guess based on our sample, but is it the most accurate? So if you want to be more accurate, you could perhaps report a range. That's when we say we are confident our population mean is between X and Y, or Y and X. All right, so we give a range. Now, obviously, the bigger the range, then go a smaller range, we're less confident. Give a bigger range, more confident. But it's a trade-off. Bigger range is not very helpful. If I went to my boss and said, suppose I went and asked my boss for a raise. I said, hey, can I get a raise, please? He's like, sure. Like, the smaller the range he gives me, he's like, I gotta go run the numbers, but you can be pretty confident it's between, $2 and $4 an hour. Right? That's helpful. I'm like, okay, on bottom. But he also could be wrong, right? He could go to the board and they could look at the numbers and be like, yeah, we can't quite do that range. He's less confident in that range. Now, if he wants to make sure he's not wrong, he could say, well, you can have, I'll talk to the board and you can have somewhere between 0 and, $200 an hour. Well, yeah, wow, that's a huge range. What do I plan on? Do I plan on 0? Do I plan on 200? Do I plan on 100? Like, this is pretty significantly different here, right? So this bigger range, well, he's more confident. He's not going to be wrong, because if they come back with nothing or they come back with an excessive amount, he's going to be right either way, but it's not very helpful for inferences or planning. So the bigger the range, the more confident we are that we're correct, but the less useful it is. The smaller the range, the less confident we are we're correct, but the higher use it could potentially be, but we could also be more likely to be wrong. So what happens here is we have proven that if you take a sample, and you know what distribution that sample comes from. And we're talking about samples and means usually. Because we're talking about means, we know from the central limit theorem from last term that these means are all pretty mounded shaped, with the mean of our population mean is the same as our sample mean kind of thing. our sampling distribution mean is the same as our population mean, and our sampling standard deviation is the same as our population standard deviation divided by the square root over the sample size that we take. All right, so we know this is true and it's pretty bounded. And we also know how we can find what percentages of the data is in between this. Like we know how to find these cutoff points. That's why we worked so hard on it last week. So we can find these cutoff points. And if we take a sample mean and say we want to be 90% confident, we can take that sample mean and we can add or subtract a margin of error. And when we add, then we get an upper limit. And when we subtract, we get a lower limit. Okay. Now, how do we calculate that margin of error? Well, we look at what the standard deviation is, how many standard deviations away we need to go. How many standard deviations away do we need to go to get this percent of the data inside? All right. So if I want to be 90% confident, that's about what is that? Well, it depends on our sample size, right? Because anyway, we'll say it's, approximately let's do 95% because that's the empirical rule. It's about 2 standard deviations or 1.96. Right? So I'm going to take my sample mean, subtract, and then I'm going to take about 2 times my standard estimate of the error. And this is my margin of error for 95% confidence. So what's the 95% confidence means? It means if I repeated this process, here's the population mean. Notice the population mean doesn't change. It never changes. The population mean does not change. We're not catching the mean it doesn't change 95% of the time it's here and 5% of the time it's not there. The population mean doesn't change. It's a constant. Right? But if I took a whole bunch of samples and I calculated the confidence interval with the lower limit here and the upper limit here, and I did another sample and I did the same thing, and I did another sample and I did the same thing, and I did another sample and I did the same thing, right? 95 out of 100 times that I did this, the process would work. And the true mean would be within this upper and lower range. But 5% of the time, the process would fail me. And the confidence interval would miss the true mean. Right? So 95 out of 100 times, I end up capturing the mean within the upper and lower, encasing it, but 5 out of 100 times, I miss it. Okay? So that's what the idea of a confidence interval is. Now, it turns out we can build these confidence intervals for lots of different statistics. Like I've been talking about, we can build them for means. Okay? And if we know the population standard deviation, then we can use a normal curve. We can build them for means, and if we don't know, the standard deviation, then we use the t-distribution, which you learned last week. That's how the data is going to fall. Now, both of these look pretty much the same. It's a little bit more area on here, so it's a little bit more robust, less likely to be wrong because it's a little more conservative, and therefore that's why I use it when we don't know sigma. We can build these for proportions, right? And when we build them from proportion, that's like using a binomial. If we want an exact, we would use a binomial distribution. But more often than not, we just use a normal curve to approximate that. You might remember doing that last term as well, like when we were looking at binomials and normal approximations, right? And we can also build them for standard deviations, and this uses a chi-square distribution. So we can build these different types of confidence intervals for these different parameters of our population. And these are the assumptions that we're making about these parameters, the distributions. I will be available on Wednesday night to go through all of your questions. Your technology is going to be a big help to you, so make sure you have Minitab available or your TI out. The more you use that TI, especially in this chapter, the faster and the more convenient you're going to find your homework going. Hope you guys have a great week too, and I'll see you on Wednesday night.